take a break of 30 seconds and I'll be back. Okay, just wait for a moment. I'm just making the things ready, so it will be done. Let's check if the video orientation is okay or it has been readjusted further. And then I will start. I think it's on. So let us start. Till today, I'll be mostly talking on the optical properties of nanomaterials. So, before going into details, the materials are classified into three broad categories: metals, insulators, and semiconductors. In this lecture series, I'll be discussing about the optical properties of materials in nanoscale for all in three different sections: optical properties of metals, optical properties of semiconductors, and dielectrics in nanoscale. So, mostly our lectures will be focused on the semiconductor and metallic nanostructures. And as you know, these semiconductors and metal nanostructures and their composites are of really great interest because of their unique and unusual properties like absorption, photoluminations, and various nonlinear optical properties like second and higher harmonic generation, etc. So, these properties are really very fascinating and useful in various kinds of optoelectronic devices. And as you know, in nanoscale, due to small size, the carriers, if we say electrons or holes, these are mostly confined within a very small size of the nanocrystals. So this confinement effects influences the energy states of the carriers, their band structures, and directly influences the electronic properties of those materials. So therefore, we can just say that the critical parameter that influences these properties are the particle size, shape, and surface functionality of these nanomaterials. So, just let me give an example. The gold. When gold is in bulk state, its color is golden, or what we say yellow type golden, right? But if we prepare gold nanoparticles or colloidal solutions, and the size of the gold particles be 30 nanometers, then there is a phenomena called surface plasmon resonance that happens, that makes the blue green color absorbed by this nanoparticle and they reflect the red light. So what you get? You will get a rich red color from those gold nanoparticles. Although in bulk state they were yellow. Okay, so these colors of these metal nanoparticles uh, is mostly happening due to the resonance oscillation of the surface electrons interacting with the external photons. So this is what is called the surface plasmon resonance that I will be explaining in details. Now, if you go on increasing the particle size, there is a shift in this plasmonic resonance spec. Okay, and as a result, these gold solutions, so that is the colloids, will appear pale blue or purple color. But if you take a gold colloids which size is below 3 nanometer, then the color is simply transparent. So the gold is golden in color only in bulk state, but if you go for nano state, its color basically depends on size. Okay. So then what about the effect of particle size on semiconductors? Right? You know, semiconductors are mostly characterized by their band gap. There is an energy gap between the outermost field valence band and the topmost conduction band. That is what is band gap. So there are two types of semiconductors, you know, one is direct band gap and another is indirect band gap semiconductor. So in a direct band gap semiconductor, when the carriers are excited from conduction band to valence band, then when the carriers from the valence band, conduction band, get de-excited to valence band or any other deep level states that I will be discussed in the next section. So during this downward transition, photons are emitted. So this photons emission mostly happens in case of direct band gap semiconductor, like silicon, like you know, gallium arsenide, indium phosphide, zinc oxide, cadmium sulfide, etc. And at this point, it's very essential to remember. I think all of you know that silicon and germanium are indirect semiconductors. Okay, so if you take the example of cadmium selenium quantum dots, and if the dot size is 2.3 nanometer, if it is excited by a UV light of wavelength 365 nanometer, it appears strong blue. Okay, so basically you will see a blue color. However, if the cadmium selenium quantum dot has a size about 5.5 nanometer, then this emission is in the red region, right? So how this happens? The origin of these specular optical properties of these semiconductors depends on various factors such as mostly the particle size, shape of the nanoparticles, its energy band structures, density of states, existence of various shallow level defect states that may be created between the conduction band and the valence band, and also in case of metals, the surface plasmon resonance. Okay, so in the foregoing lecture series, I will be mostly explain all these phenomena in detail for a from a very beginning, so that any layman which is who have a very basic understanding of various physical phenomena like quantum mechanics, mostly the Schrodinger equation and its solution, and the various physics such as the band structures of solids, and the various different kinds of energy models of metals, they will understand this lecture. So this lecture is mostly suitable for undergraduate and postgraduate students, and also will be going to be a very useful lecture for those students who are studying their PhD coursework in the very initial stage. Okay, stay tuned with me and you will be updated soon.